Hello, everybody. Good morning. Welcome to this SBDM number 11. Yeah, just one big thank to our main founder, which is the demon Seabrains. And so a bit of explanation for the format this year, because you've noticed it's a bit shorter than usual. This was meant to be an effort to reduce the carbon footprint. May not be the most optimal solution, but that's what we've decided. And we've also decided to invite people from neighboring countries so they don't have to fly and pay the carbon cost. Nevertheless, we have a great line of speakers. We have four sessions of talks. The first session this morning is about artificial neural networks and how they make decisions. It was supposed to be chaired by Kenji Doya, but unfortunately, poor Kenji got a bike accident, so he could not make it. But we have an excellent new chair, Alizée Lopez-Persem, and yeah, let's get started, Alizée.
Thank you, Matthias. You said it all almost. Yeah, so we're going to start this first session. I'm very happy to chair the opening session of this 11th SBDM. And we're going to hear 4 speakers about how artificial neural networks make decisions. And so we will hear Christopher Summerfield, Florent Méniel, Vesa Boboa, and Jean Denisot. And I'll make very short introduction and be sure that we stick to the time schedule. And I'm very happy to introduce Chris Summerfield. So he's professor at the University of Oxford. He's also a research scientist at DeepMind in London. And Chris is going to talk about control, more about how artificial neural networks can control themselves. And we are very happy to have you here, and thank you very much.
Okay, fabulous. Can you hear me? Yeah, so it's such an honor to be here to open everyone's favorite conference. I think this is even the favorite conference of people who don't know about it yet. So it's really an honor. And I've taken the opportunity to talk about a new project. And this project is led by Kai Sandbrink, who's here today, and he has a poster about it as well. So if you get bored or go to sleep, you can also go and see his poster. So the project is about self-control. So self-control is important, which is something that I've learned to my cost over my life. I think it's something that when we think about from a computational perspective, often we overlook. So we're in France. So here's a nice French example of self-control being necessary. So this is Philippe Petit, I think you all know, who famously crossed a wire, but walked on a wire between the Twin Towers when they were still there. And so, as he was embarking on this death-defying endeavor, of course, he was assailed by different sources of variability, which could have been kind of led to really negative outcomes. So the first one is that, of course, he had to choose where to put his feet so that he didn't fall off the wire, right? And this is a hard task because, as we know, mechanisms of action selection, like all neural computation, are subject to internal variability or noise due to the intrinsic stochasticity of neural process. And so what this means is that, he has to be able to control his actions in such a way that, he doesn't put a foot in the wrong place. But of course, at the same time, he's assailed by external variability. So in the case of the Twin Towers, which are quite high, this takes the form of wind, for example, which can buffet him from side to side. And so the actions that he takes could also be erroneous because of factors which have nothing to do with him and his action selection processes. And so when we're learning how to behave, it's extremely important to be able to distinguish between these sources of variability. And the reason why it's so important to distinguish between them is because, of course, we can do something about the internal sources of variability by exerting control processes or attention to try to essentially to mitigate the effects of that noise. But in the case of the external variability, we can't do anything about it. So we need to be able to tell them apart. So let's try and think about sorts of computational frameworks that we have built to try to understand these processes. So here's one which would be a natural way of thinking about reward guided or any process. I mean, obviously you wouldn't want to learn to tightrope walk by trial and error, but like any process in which, you know, kind of there's a positive or a negative outcome ensuing from your actions. So reinforcement learning, of course, gives us a framework for thinking about this. And in reinforcement learning, there's a dyadic interaction between the agent and the world that involves a threefold exchange of information whereby the agent receives observations from the world and then selects actions which are compensated in various ways with an outcome, can be positive or negative. So clearly, and during the process of you know, our frameworks for understanding as a methodological toolkit in both neuroscience and in AI research, reinforcement learning gives us ways of thinking about the internal representations which are formed in order to learn an optimal value function, in order to choose something that will allow you to choose the best actions, which would be, you know, for example, not falling off the wire. But of course, you know, kind of in this framework, there's no natural way of thinking about these two sources of variability that I introduced. In fact, all you have is you have an action and then you have a reward from the world. So how do you know if you get a negative outcome? How do you know whether that outcome was due to something that you did wrong, internal variability, or something that happened externally in the world? There's no natural way to think about this, right? So, you know, we might want to think about maybe a more kind of realistic way of modeling this is that when we take actions, you know, there's some probability. We could model this in a very simple way. In fact, I'm going to show you a way where there's just some fixed probability that your actions are wrong, something that's called epsilon greeting. But there's a fixed probability that some nasty demon kind of intervenes. And even though you've selected the leftmost action, you actually end up taking the rightmost action. So we're going to use this type of framework to try to understand these different, how computational models can learn to control themselves, so can learn to distinguish these two sources of noise and to essentially to mitigate the cost of internal errors. And the framework we're going to do that in is, because this is a session about artificial neural networks, we're going to use a way of implementing reinforcement learning, which is not kind of the standard way that many of you will be familiar with. You know, kind of when if, for example, if you're interested in modeling a bandit task, then you would probably use a computational framework in which you would decide exactly what the states are, what the internal states are. For example, you might construct a table which says, you know, the agent is going to learn the value of one bandit or the value of the other bandit. But instead of doing that, what we're going to do here is we're going to use a toolkit from machine learning in which reinforcement learning is implemented in a neural network. And specifically for those of you who know about it, we're going to use a toolkit called policy gradient methods. Okay, so here's the task that we've used. So I invented this task and I was enormously proud of my own creativity until Kai pointed out that it had actually been invented in 1966. And so that sort of diminished my my hubris somewhat, but I do think it's an excellent task. So in this task, it will be familiar to those of you who know the sort of standard bandit framework. So there are two possible outcomes. You have to choose between two possible outcomes, and these outcomes they're like slot machines that pay out with some fixed probability. But in this task, you have an alternative option. And that's signaled by the glasses in the middle. And if you choose the glasses, then in this task, rather than receiving an outcome from one of the two bandits, rather what happens is that you are informed of which of the two bandits would have paid out if you had chosen it. So in this case, there's always one bandit that pays out and one that doesn't. And so in this case, if I choose the glasses, it tells me that the blue bandit would have paid out, but I don't get any reward. So in this task, choosing the glasses or the observe action is a pure exploration action. It has no reward benefit, but it gives me purely information. Alternatively, I can choose one of the bandits. So for example, if I choose the blue bandit, then that bandit will pay out or not. But critically, if I choose the bandit, I don't get to see whether it's paying out or not. So I'm blind, right? And this is called a bet trial. This is called the observe v bet trial. And as I said, it's been, not only was it invented by Amos Tversky, it's been used by in a number of different labs, including recently in an imaging study from Sam Gershman's lab. The twist which we've added to it is shown by the demon up there. So in the BET trials, and in BET trials alone, rather than your reward always translating exactly to the choice that you made, sometimes the demon's going to intervene and force you to choose the other option, right? Nasty demon. But of course, because this is a BET trial, you're not actually going to know that that's happened on this trial. So you're going to have to infer it. You're going to have to infer it from the whole sequence of rewards that happen over the entire block. And so what we do, just like in other variants of this observe be bet trial, observe be bet task, is at the end of a block, in this case for our human subjects, a block of 50 trials. I think for our neural networks, we have 100 trials. The participants get a full representation of all of the decisions that they made, including those bet decisions, and post hoc at the end of the block can see whether they were successful or not. And so the idea is that over many blocks, and this is what's shown in previous studies, over many blocks, people should be able to optimally, well, in the standard task, people should be able to learn to optimally learn an observation policy, like when it's good to explore rather than to exploit. And in our hands, there's going to be the additional twist that people are going to have to learn that policy conditional on the behavior of the demon. And what we're going to do is we're going to control the behavior of the demon via a single parameter, which we call efficacy. And this efficacy is just going to be a fixed flip probability. It's going to be a probability that the action that you chose gets translated into something that you didn't choose. So this is the setup. Here's our model. So as I said, our model comes from a sort of suite of methods known as policy gradient methods. This is reinforce, straight reinforce. And so basically as inputs, the model is going to receive basically a bunch of stuff, but specifically information critically, not any information about the observations, but the action that it took. And also in particular, it's going to receive information about the action that it chose. So we're going to assume here that the network can kind of see that if it chose A, but actually the daemon switched it to B, that's there implicitly in the network's inputs. These inputs are going to be passed through a form of recurrent memory called an LSTM, passed to a recurrent network, and then they're going to be used to drive a policy. And that policy is going to be essentially something that spits out the probability of an action given all of the inputs. We're going to train this network using policy gradient methods, using reinforcement learning to try to maximize the reward that it obtains, which in this case is going to be, you know, kind of the greatest probability of choosing a bandit that pays out rather than one that doesn't. Okay. So using this framework, of course, this is we're doing machine learning here. And so, you know, kind of one of the opportunities that affords us is to dissociate the training and test conditions. And so what we're going to do is we're going to train this network in a variety of under a variety of different efficacy levels. And our first question, our main question, is going to be, what are the conditions that are going to allow a network like this to learn to generalize what it has learned during the training under one set of efficacy levels? What's going to allow it to generalize to a new set of efficacy levels? So in other words, we're going to ask the network, it's now faced with a new block. It doesn't know what the demon's going to do on this particular trial. Is this a really nasty demon or only a slightly nasty demon? And it's going to have to learn from the pattern of actions and outcomes and those observations that it gets at the end of the block. It's going to have to learn to try to observe or bet in an optimal fashion. Okay, and so the first thing that we can see is when we train this network, and this is just averaged over all training conditions, including conditions in which the efficacy is low and conditions in which the efficacy is high. I think this is actually training data. And the first thing to show you is a null result. And that is that a network of this form just simply cannot learn this task. And the reason why we know it can't learn this task is because what the network's performance or its reward level in the block converges to a reward of 25. So for the neural network, there's 100 trials in the block. And so getting a reward on 25 of them is exactly what you would expect by chance. And so is it what you, oh no, sorry, there's 50 trials and getting a reward of 25 is exactly what you would expect by chance. So, you know, kind of basically the network is not doing any better than if it just closed its eyes and chose at random, right? So this, of course, might be just because we're really bad at machine learning. I'm going to show you, I hope in the future, that's probably not the case. So thinking about this problem, Kai brought a really, I think, fantastic intuition based on his reading of the literature to, how we might be able to think about what the necessary computational steps are for solving this problem and allowing our network to do a little bit better. And it comes from reading of a bunch of papers. Here are just 2 of them, although there are many other papers in this vein that have been published recently that try to distinguish in the field of the computational models of decision-making, try to distinguish between learning which is conditioned on actions and outcomes, and learning which is purely conditioned on actions, right? And some people call this goal-based and habit-based, or sort of value-based and habit-based. But broadly, the intuition is that, of course, in the standard RL framework, something like temporal difference learning, then what we're going to learn is we're going to learn a Q function which says, what is the value of taking this action in this state, which is obviously something very useful to learn, right? But of course, if I am in the same environment over and over for lots and lots and lots of trials, and I've learned an optimal value function, I don't actually need to know what the state is anymore. I can just rely, at least on part, I can just rely on those actions that I've taken in the past. So habits are a heuristic that the brain uses in which it says, okay, well, I've used this action a lot in the past, so it's probably a pretty good strategy. So I'm just going to use this action again in the future. So in these models, this is a model by Kevin Miller. This is a model by our colleague Raphael Bogarts in Oxford. And in both of these models, there's these sort of dual value and habit-based processes. And Kai's intuition was that maybe by learning the value, but maybe by learning the simple probability of selecting an action. So in this case, which corresponds here to an attempt to predict the efficacy in each block, then maybe the network can solve the task. So what we did was something extremely simple. And that is, from the LSTM, via a single node, we try to make a prediction about what the efficacy is. So this is simply the probability. It's like we call it an action prediction error, because it's the probability that the action that you take translates into the consequences that you intended, right? Like, essentially, how habity are your actions, essentially. And, of course, over the course of training, a network equipped with this one node can learn pretty well to predict what the efficacy is. And lo and behold, when the simple addition of this one unit is able to transform the network from basically not being able to solve the task to being near optimal on the task. That's shown as by the blue line here. And it's not only good at training, which we might expect because that's what we've trained it to do, but it's also good at evaluation. So what that means is that even if you give it a set of conditions in which there's an efficacy level that it hasn't seen before, it's able to optimally adapt to say, hold on, here my actions seem to not be translating into their consequences about this much, about X amount. And so the network can then adapt its policy and perform really quite well. So another perhaps stricter test of what the network is doing is that, of course, if we are able to understand the levels of control that we have over the environment, then this should translate into the degree to which we explore or exploit. And that's, of course, it's kind of obvious if you think about it for a while, because if the environment if you have very, very low efficacy, so in other words, the daemon is just switching your response on every single trial, so that even if you're not being random, the daemon is making you random, there's absolutely no point in exploring. The best thing you can just do is close your eyes, choose options, and hope for the best. So a network should learn to explore very little when the efficacy is low, and as the efficacy grows, it should learn to explore more and more. And this is exactly what happens in the case of the networks that have this APE unit, but not in the case of the vanilla networks that lack this one extra unit. And of course, this idea is not our idea. It relates to canonical work by Quentin Hoyes and Peter Dayan from nearly 15 years ago now. Sorry, so this is rewards. I had the wrong thing on the y-axis. This is rewards, and this is the probability of observes here measured by simply the probability that they choose that observe option as under each efficacy level. And if we look in a little bit more detail about what the networks are doing, it's quite informative. So you can see that here, if we just look at over the block of 50 trials, if we look at the pattern of observes that the network is making, you can see that what it does is it takes a peek at what the values of the bandit should be early on in the trial, actually probably 2 peeks it's taking, at least in some trials. under different efficacy levels. And then, you know, kind of over the course of the trial, what it's doing is kind of like cyclically sort of rechecking. And the reason why it's cyclically rechecking is for a very important aspect of our task, which I'm sorry that I forgot to tell you, which is that there are occasional switches between the bandits, making it a good strategy. You can't just observe once and then bet ever after. You have to check from time to time to see whether the experimenter has flipped, has reversed the payout probabilities of the two bandits. And you can see that our no APE network, which differs only by one node, of course, what it does is it just observes at the beginning and then bets forever after, which is, of course, you know, a fairly terrible strategy. We can also see, you know, kind of, this is also, thank you, also clear in the number of correct takes that the network has. Okay, so maybe I'll skip this. So we've also done another task in which the network has an additional, this is a slightly more interesting task in which the network has an additional option. And this is an extra action which the network can take that we call the sleep action. So in the sleep version of the task, the network can actually choose to increase its own efficacy, a bit like you can increase your efficacy by having an early night. And the network will then, we can show that with this APE, but not without this APE, the network will then learn to increase the probability that it sleeps as a function of how low the efficacy is. So when the efficacy is low, it knows that it's really tired, it needs to sleep to increase its efficacy. It does that really well. And I'll skip this. Okay, so just in the last minute, I just want to tell you about some very preliminary human work that we've done in this. So Kai has built a sort of 2-day human experiment, which uses the observe v bet task in association with task 1, not the sleep task, just the generic task. And our preliminary results so far is that participants with a bit of nudging, they can learn to do this task, and they can learn to do this task in a way which is qualitatively similar to the neural networks, in that they will learn to both do better when the efficacy is higher, and perhaps more interestingly, they also learn to observe more when the efficacy is higher. So you can train them to do exactly like the neural networks, or like the neural networks with this APE training. But the most interesting thing, I think, from our perspective is a link which we've tried to make to different psychological disorders, which might emerge that this task might be an appropriate way to index. And the reason is because we can take different approaches to try to give the network false information about that efficacy. So, of course, remember, the network's learning to predict the efficacy on each block. And one thing we can do, the easiest one to explain here is the one on the right. So what we can do is we can simply give it misinformation about how likely it is that, about how successful their actions are in translating to their consequences. So in other words, even if the efficacy is low, we can give it a feedback signal that says, no, the efficacy, you're doing fine. The efficacy is quite high, or vice versa. And when we do that, what we can see is that we get stereotyped patterns of pathology in the network. So they can be shown here. And so, you know, kind of under healthy function, which we've already seen, that's the black line, we see that the number of observes grows with efficacy. We've already seen that. That's the Huizen-Dayan finding. But when we essentially tell the network that their actions are translating into their correct consequences too much, then the network kind of becomes really, really compulsive and starts observing all of the time, even under situations where it's a terrible idea to observe, which is when the efficacy is low. On the other hand, if we give it the wrong information in the other direction, so we tell the network that its actions are actually quite bad, that its actions are not translating to their intended consequences, even when they are, then the network will exhibit something that resembles what we might call learned helplessness. So in other words, even when we now start giving the correct information, it you know, kind of makes no attempt to control its environment and just sort of sits there. It's like, oh, this world is horrible. I'm not going to try and do anything. So just very briefly, sorry for the horrible slide, we see similar variability in our human participants. And so we've, collaborating with Lawrence Hunt, who's over there, we have, you know, we've begun to try to take measures of anxiety, depression, and compulsivity from our participants. We still only have a relatively small cohort, but what you can see is that there are at the moment, very marginal, but you know, perhaps things will improve when our cohort gets larger, marginal relationships which are broadly in the right direction. So for example, you know, this anxiety score, the slope of the slope of that relationship between probability of observing and efficacy is steeper for people who have low anxiety than have high anxiety. So in other words, this is exactly the effect that we would predict. We do see an effect in the expected direction for compulsivity, but it's not significant. And that's it. So I really want to highlight Kai, who led this work. He's done an absolutely marvelous job. Thanks, Lawrence, for input as well. And thank you all for listening.
Thanks for the great talk. I was wondering whether you could speculate on what areas might be involved in these false feedback.
Yeah, that's a fantastic question. So maybe someone who actually knows something about neuropsychiatry could answer that question better than me. I don't know. I mean, I guess that, you know, kind of in the framework which has been developed by people like Raphael Bogarts and Kevin Miller, you know, the habit-based system is clearly associated with, like, you know, kind of basal ganglia, corticostriatal loops, right? And, you know, kind of the idea is that there's a sort of parallel habit-based system, which perhaps involves more dorsal structures, whereas the value-based system perhaps involves more ventral structures, like, for example, the orbitofrontal cortex. But, you know, when we discussed this work with Raphael, he's pointed out that, you know, kind of our prediction of efficacy, like our notion of an action prediction error, like how accurate how likely is it that this was a good, that this action that I took translated into the consequences which I intended it. That is kind of, it's not exactly the same as the habit-based signal, right? The habit-based signal, which has been shown to kind of stabilize learning in value-guided systems, is possibly, you know, kind of perhaps it happens over a longer time scale. You know, here, you know, in many situations, you sort of dynamically have to try and work out whether your actions have their intended consequences. So social behavior is the hardest one, right? We're doing this all the time. When you're talking to someone, you're like, am I making sense? Is this person like actually understanding what I'm saying? Do they think I'm an idiot? Like we're doing that all the time. And we're doing it like in the observe v bet task, because we don't get direct feedback about the consequences of our actions because they're happening in someone else's head.
Please, I actually have a question about the healthy function that you showed on the graph. I was not sure this was meant to be the optimal strategy in the task. So the first question is, can you or can't you derive what is the optimal strategy in that task? And if yes, how do you define the cost of cognitive control? So is it just an opportunity cost? So it's the cost of not betting when you observe, or is there anything else?
Yeah, so I mean, in theory, the neural network should learn the optimal policy, right? I mean, in the limit, right? But we don't know what the theoretically optimal policy is. Theoretical, I mean, it's kind of difficult to calculate. We can, under some assumptions, and Kai has done this in a kind of Bayesian model, try to work out some kind of like bounds on what we might expect the maximum reward to be if you did some sort of, you know, really clever lookup process where you imagined every possible outcome for every possible observed v-bet choice. But it's definitely true that that qualitatively it is optimal for your choices, for your probability of observing to increase with the efficacy for the reason that I described. So that's probably a slightly unsatisfying answer to your question.
Still answer. Thanks.
Okay.
Thanks for the great talk. My question is about the additional node to tracking the efficacy. How it does it can help to adjust to the novel environment, like when they just suddenly drop to the new environment with a different level of the uncertainty, then can they helping to adapt to the new environment?
This is a super question. And this is for me, I skipped over this slide, although it's perhaps the most interesting slide of the whole talk. So what this slide shows is that, so the way we set up the network has all the information it needs to solve the task, because we provide to it in its inputs both the action taken and the action chosen. So all the network has to do is compute the discrepancy between those and learn that when they're discrepant, like things are messing up. And like, because things are messing up, you know, you probably need to dynamically adjust your observe v-bet strategy. So the network has that information. And in fact, when we try to decode efficacy from the neural network, we can decode it even from the non-APE network. And that's what's shown in orange here. So over the course of training, it's slower, but it reaches the same plateau In other words, kind of the network has the relevant information and it represents the relevant information in the hidden layer, which is really surprising, right? So what is the point of this one clever node, right? So clearly what it's doing is it's like in some way making explicit that efficacy information. It's like saying, the prediction errors that you get when it's like, kind of, I think I'm doing really well, but you're actually getting a signal which is like, no, you're not, you're doing really badly. That really makes that information available to the network in a way which it can then use it to adjust its policy. And for some reason, which we don't understand, having the information merely through the inputs, it does not do that.
Thanks for the great talk. I'm a little bit puzzled by the way you formulate it. I think it's nicely illustrated on the slide. This is as your daemon changing the action that you take. When I think about whether you have control and efficacy of your actions, this is more about whether the actions that you take lead to the outcomes that you want to get. And so I was curious whether that's relevant or whether that's just, you can like quite just as easily reformulate this as about being outcomes. Because when I think about, I don't sort of, when I intend to go left, I don't accidentally go right, but I might not end up at the place that I would want to be.
Yeah.
And also when you think about learned helplessness type paradigms, then really that's about, do your actions lead to the results that you want to get to?
So I think you're absolutely right. There's a variety of situations where there's a sort of really blurry line between these internal and external cases, right? And the example you give is a fantastic one of where, kind of if I'm navigating, clearly if I mess up, it's not because I like moved the wrong foot or something like that, right? But if you were playing tennis, if you're trying to do the perfect serve, then it might well be the case that the failures, the reason why you hit it out and failed to win Wimbledon, was actually due to some internal process, right? Our actions, however much we intend the serve to go in, or, kind of however much we intend, exactly things to come out in exactly the right way, sometimes they don't. And, I think that, it's true that, yes, it's true that there's a blurry line between the two, but I think that, you kind of, I know will know the learned helplessness literature better than me, but I think it's at least reasonable to assume that if we're getting incorrect feedback about, how well our actions are translating into their desired consequences, then it's reasonable to assume that that would have a detrimental effect on our propensity to then be motivated to select those actions and think that we're doing really well. But I think you're right. I think you're right that, kind of control processes operate in different, what does it mean to exert control to, I don't know, be more eloquent, or exert control to do better in an exam, or exert control to, kind of run a marathon and beat your personal best. What does that actually mean? I think those cases lie at the intersection between that internal and external.
We have to stop here. Thank you very much.
Thank you,
Chris.
Alizée.